Okay, this is the November 2017 Physical Science Paper 1, Multiple Choice Questions, Paper 1. It says the acceleration due to gravity on Earth is greater than the acceleration due to gravity on the Moon. Which one of the following statements is correct? The weight of an object on Earth is the same as that on the Moon. No, this is incorrect because how do we calculate weight? Weight is equal to mass times the acceleration due to gravity. So this one is wrong, and this one, the weight of an object on Earth is less than that on the Moon. This one is also wrong because on Earth the gravity is bigger, so the weight is bigger. But the one we are looking for is B. The mass of an object on Earth is the same as that on the Moon because why? What is your mass? Your mass is the number of particles that you contain, and unless somebody chops off your arm on the way to the Moon, you will have exactly the same mass on the Earth as on the Moon. The force diagram below shows the forces acting on a box. Which one of the following equations for the magnitude of the normal force is correct? Okay, in this situation, to calculate the normal force, you have to say that this box is, if we look vertically, okay, this box is in equilibrium. Okay, we say up is positive and the box is in equilibrium. So what forces do we have up? The normal. What forces do we have down? The weight. And now we've got this force F which is being applied at an angle, and that means F is made up of a vertical component Fy and a horizontal component Fx. And from trig we know that Fy is F sine theta. Okay, so vertically this box is in equilibrium. So if we say up is positive and we make a little sum of the vectors, okay, if it's in equilibrium there's no net force, or you can say forces up equal forces down. What forces do we have up? The normal and the y component of the applied force. And then what forces do we have down? The weight. So we're going to add the weight, but because the weight is negative, it becomes subtract the weight. Okay, so if we want to find the normal force, we want to get the normal by itself. So we'll take the weight over and subtract Fy, the y component of the applied force. So what will my normal be? The weight minus F sine theta, which is giving me the answer D. The normal is the weight minus F sine theta. And we know this because the normal is used to calculate friction. If you try and pull a box with a force acting upwards, it's much easier than to try and push a box with the same force acting downwards, because when we push downwards on the box, we increase the force of friction because we are altering the normal force. Now it says to you, a stone is projected vertically upwards from the top of a building at a speed of v meters per second. The position time graph below represents the motion of the stone. Ignore the effects of air resistance. So we know that this is a projectile. And what do we know about projectiles? The only acceleration is the acceleration due to gravity, which is 9.8 meters per second, downwards to the center of the Earth. So they love to ask questions about what do you realize about the acceleration? Which one of the combinations below regarding the magnitudes of the stone's velocity and acceleration at time t1 is correct? Well, you can see this is a displacement graph. What is at time t1? This is maximum height. At maximum height, the velocity has a magnitude of 0. So we're looking at these two answers. Just because your velocity is 0 does not mean your acceleration is 0. Your acceleration is 9.8. The Earth never ever stopped attracting that stone, and the Earth is what causes it to accelerate. It's what caused it to slow down when it was going up, and it's what causes it to speed up when it's going down. So the answer is A. Never ever forget when and where the acceleration is. Now here we have a momentum question. A trolley of mass m is moving at constant velocity v to the right on a frictionless horizontal surface. A ball of clay, also of mass m, dropped vertically, falls onto the trolley at time t as shown in the diagram below. The ball of clay sticks to the trolley. So we have here a collision in terms of momentum laws. And they've told you that there's no friction, so we can assume we've got an isolated system. Which one of the velocity time graphs below correctly represents the velocity of the trolley before and after time t? So we know that if momentum is conserved, the sum of my initial momentum is going to be equal to the sum of my final momentum. So if we're looking at the horizontal velocity of the ball of clay had no velocity, okay, horizontally. Yes, it had a velocity falling downwards, but if we're looking at the vertical velocity, there was none. So for the ball of clay, the P for the ball of clay was 0 initially, okay, because it's not going in the direction we were going. But the trolley had a P of mv for the trolley. Now, after the collision, the trolley is going to move off and it is going to be 2m. So the sum of the momentum before is equal to the sum of the momentum afterwards. So this means that for mv to be equal to 2m, the v must have got smaller for the equation left-hand side to equal the right-hand side. With this question, remember that velocity is a vector, okay? But when do we get a minus v? We get a minus v when you change your direction of motion. So this one is saying I was going at this velocity forwards and now I'm going at this velocity in the opposite direction. And that is not what happened in this collision. The trolley just kept moving in the same direction. We only have one v. So this one is clearly out. And this one, which is slightly more correct because it shows a decrease in velocity, is also out. So the trolley had to slow down when it got more mass on it. So the answer is C. This one is showing you both of my velocities are in the same direction, but my initial velocity was a larger vector than my final velocity. So the answer is C. Now we've got a question where they're trying to confuse you with work, energy, and power. Remember that power is the work done per unit time, and work is equal to the force times the displacement times the cos of the angle between the force and the displacement. Okay, so it says to you, a person lifts a crate vertically upwards. So here is the ground, here is the crate, and the crate is going upwards at a constant velocity through a height h. Okay, the person does work x on the crate. So the work is equal to x and the time is equal to t. So if they're giving you time, you're thinking you're dealing with power. Okay, but that is not what this question is asking. Here is the crate now. We're lifting the same crate. We are lifting it vertically upwards at a constant velocity through the same height. Okay, it says through the same distance. So the h is the same, but the time is now 2t. So they did this one slower. Okay, but now the question says to you, what is the work done by the person? They've given you all of this time information, but they did not ask you about the power. It is only the power formula that deals with time. The work formula just asks, how far did you move it? Okay, so the answer here is still the same work x was done on the crate in time t, because we displaced the crate exactly the same distance, and the force we're working against is gravity. So the work done against gravity is 100% exactly the same, even though we did it slower. If they asked you about the power, you could think again, but they don't. They say, what is the work x? 1.6 is a Doppler question, but it's a Doppler with light, okay? The wavelengths of light emitted by a distant star appear shorter when observed from Earth. From this, we can conclude the star is. Now, remember when we talk about the Doppler with the stars, we talk about redshift and blue shift. So if we write the colors of the rainbow or the spectrum, whichever you prefer, here is red and here is blue. So the blue end of the spectrum is actually the high frequency, and the red end of the spectrum is the low frequency. So we know V equals F lambda, or in this case, because we're talking about light, C equals F lambda. So frequency is inversely proportional to wavelength. So a high frequency has got a short or a low wavelength, and this one has a long wavelength. So if the wavelengths of light are shorter, then you are going towards the blue end of the scale. So we only want the answers with the blue shifted light. And how do we increase frequency? We have to increase frequency when objects move closer together. So the answer is here, A, the object is moving towards the Earth, and the light is blue shifted. We usually talk about red shifting as proof that the universe is expanding. Distant objects are red shifted as they are moving further from us. But some objects do actually move closer to Earth, and they will show a blue shift. Okay, 1.7, the first thing you do when you see spheres is you tell yourself, like charges repel. So before I read a word here, I can see in diagram 2 these spheres are repelling, which means they must have the same charge. Or the nature of the charge, they must be positive and positive, or negative and negative. So it says to you, two identical light graphite coated spheres, P1 and P2, are suspended using identical thin insulated threads. P1 is charged, but P2 is neutral. The spheres are then brought into contact with each other. The moment you see brought into contact with each other, we are going to use the law of conservation of charge, which says that in an isolated system, the net charge is conserved through any physical process, but is responsible for this formula here. Okay, so what happens when we bring two charged objects together? The charge averages out, everybody ends up with the same charge. So even if one is charged and the other is neutral, by the end of this, they will both have the same charge, okay? And it will be half of whatever the initial charge is in this case, because one of these numbers will be Q and the other number will be 0. So a number plus 0 divided by 2 is going to give you half of the charge, but they will both have the same charge after contact, which explains why they are repelling. Which one of the following statements concerning the charges on the spheres possibly explains why the spheres move apart after touching? So we are immediately going to rub out any answer that has the spheres having a different charge. Okay, so we are rubbing out that answer immediately. So we don't know what the initial charge was, so we can't say if it's positive or negative. But these charges after contact cannot be unequal, because the charge always averages out in a physical process. So the answer has to be D. Both spheres have a positive charge, and the magnitude of the charge is equal due to the law of conservation of charge. Now we come to 1.8. It says when a resistor of resistance R is connected to a battery of EMF E and negligible internal resistance, happy days, no internal resistance, okay, the power dissipated by the resistor is P. So if we have a look here, then it says if the resistor is replaced without changing the battery, so we've still got E, but we now have this circuit with a resistance of 2R, okay? What will happen to the power? So we must first think of what is a power formula. Power equals VI, okay? If we have no internal resistance, the voltage on this one is going to be equal to the EMF, and the voltage on this one is going to be equal to the EMF. That's what it means when it says there is no internal resistance. So if the voltage is the same but the resistance has increased, this one will have a big current and this one will have a small current, because we know that current is inversely proportional to resistance. But how much will it be? Well, if we use V equals IR and we increase the R to 2R with the V staying the same, then the current has to be a half of the current to make it mathematically equal. So if the resistance doubles, the current halves, and power is equal to the volts times the amps. So what is going to happen to the power if we halve the current? The voltage stays the same because we've only got one resistor and there's no internal resistance. So the resistance in circuit 1 and the voltage in circuit 1 and the voltage in circuit 2 are both equal to the EMF of the battery. But in circuit 2, the current has been halved, okay, which means that the power has been halved because we are multiplying by half of the current. So 1.8 is B. 1.9, have you got your hands ready in their 3 right angle conformation for which rule are we going to use? It says the diagram below shows a current carrying conductor lying in a uniform magnetic field directed to the right. So remember, we've got the 3 letters FBI, the force, the field, and the current. The current is shown with the shocking finger, yes. That finger that you shoot people a zap with is shown with the current. The force is shown by your thumb, and the magnetic field is shown by your forefinger. Okay. The trick is here, are we going to use our left hand or our right hand? Okay. So it says, which one of the following arrows shows the direction of the force experienced by the conductor due to the magnetic field? But it's telling you in the question that we already have current. Current is flowing into the page. So if we have current and a field, we must have a motor, okay? It's not specifically stated, but the current is flowing and we are determining the force. So if we are determining the force, we use a motor because motor makes mechanical energy from electrical energy. So you must use your left hand here. And if you use your left hand here, remember this conductor is going into the page, so you put your shocking zap finger into the page, you put the magnetic field, which is your forefinger, to the right, and that will show you your thumb going downwards with answer C. So because we are showing movement, we assume it is a motor. This is now the photoelectric effect. Light of a certain frequency is shone onto metal M and electrons are ejected. So this means that the frequency is greater than the threshold frequency and the energy is greater than the work function for that particular light. The same source of light is shone onto a different metal N. The electrons ejected from the surface of metal N have a higher kinetic energy than that from metal M. What does this mean? Well, we know in the photoelectric effect, our incoming energy is equal to the energy used to expel the electron plus some kinetic energy. Why did I get a half? Where do I get a half from? This is EK max. Okay, so if we are using the same light, my incoming energy is exactly the same. And this means that if the energy is the same, but the electrons have an increased EK max to make this mathematically equal, the work function must be less, okay? So is there one that says one has a smaller work function? No, this one says the same, it's wrong. This one says larger, it's wrong, it has to be a smaller work function. Now they start talking about the threshold frequency, but we know the threshold frequency, the work function is related to the threshold frequency, basically through the E equals HF equation. So if the work function has decreased, this is a constant, H is a constant, which means the threshold frequency must have decreased. So D, the threshold frequency of metal N, is lower than that of metal M, because we're putting incoming light with the same energy, but the little electrons we are popping off are moving faster.